So good afternoon. I took the opportunity that I was here to close the contract of what has been a very big contribution from Teledyne E2B to this mission. Actually, the largest contribution probably from the Payload. And to take the opportunity, because sometimes, especially when we work with suppliers or with people, they work on something very specific, it's very focused, but you never get to see the big picture because there's never time, and we don't come around to show you where we are. So I wanted to give you just a brief summary of what was the mission science about, a couple of slides. I will not bother you too much with the science background, but also to give you a few images of where we are with the mission as a whole, because we are quite advanced. Of course, your job is finished here. There's still work to do at the spacecraft level, but it's quite advanced. So I wanted to give you a view. Very quickly, myself, I'm the mission and payload manager for Plato. I have been working in ESA for 20 years, always in science missions. My background is optics, but optoelectronics and passive photonics in the telecom industry. But then I moved to space slowly, and then since I joined ESA, I've been working in 3 missions: James Webb Space Telescope, where I was the manager of the infrared telescope, infrared instrument, a medium infrared instrument. That is the European contribution, one of the 2 instruments in James Webb. Then I moved to Euclid as the lead mission system engineer, where I did all the requirements and the design of the telescope, so on the optical side. And after Euclid, in 2017, just before we launched Euclid, but I started working in Plato as a mission and performance and operations manager, and then I took over the payload as well, and I'm still now the mission payload manager for Plato. So always in science missions, always in telescopes. James Webb is much sharper with a small field of view. Plato is a large field of view, not so sharp, so I think it goes with age. I become less sharp, but my view expands a bit. So just a bit on the science, just to recall the mission in the scope of the cosmic observers that are the science missions in ESA is here to be launched in 2026, and we are still in line for a launch end of 2026, which is very good. This was the date that we defined in 2017 when the mission started, and we are still on the same launch date, still with 4 months margin. So we are in a good situation. If you put it into context with respect to the theme, this is a mission devoted to exoplanet search, exoplanet characterization, and exoplanet finding. And there's several others in ESA that have been doing that and will do that. And I think the last one we have in ESA, Plato, in the US, they will have the Roman Space Telescope, and the Ariel mission in ESA that will do characterization of atmospheres. Same, but the focus of Plato is 3 things. How do the planetary systems evolve? Are we special? Is the solar system that we live in a particular one, or is a typical solar system within the evolution of planetary systems? And also, are there other planets potentially like Earth, habitable planets? And this is the focus, let's say, of the way Plato has been designed, is to look for planets. Let's say, let me just show you. Oh, sorry. We look for planets using 2 methods. Let's say. We just look at the stars for a long time, and if you imagine you are looking at the light of a star, when a planet goes around it, you don't see the planet because they are far away, but you see the light of the star dipping. It's not like that. It's not so obvious. It's 50 parts per million. So we are looking at very tiny fluctuations. And if it's an Earth-like a star, this will happen once a year. It's the same distance of Earth, more or less, from the star. So we have a planet like Earth at that distance from the star that allows water to exist. This is what we call an habitable planet, right? And so with a bit of luck, you see a transit once a year. So you have to have very strict requirements on photometry to characterize these very tiny fluctuations. At the same time, we look at the spectrum of the light of the star. So if you look at the light of a star over a long time, you see variations in the light emitted, that have to do with the fluctuation or the inner vibrations of the star. This is what we call asteroseismology. So if you combine these two things, you can characterize the star and you can characterize the planet. And with those two things together, you can get the orbit of the planet, the radius, the mass, and the age. We complement this with measurements with ground observatories that also tell you the distance. There's this radial velocity of the movement of the star with respect to the planet. And with these three things combined, you can characterize this kind of... Now, let me just show you one thing. We hear exoplanets all the time. They are there. There's more than 5,000 exoplanets already found. You can go there and look at them. But most of them are in this regime. These are the already found exoplanets, but they are either very big, type of Jupiters, or some that are very close to the star, because then we can see easier this obscuration. You see, there's not many here, which is in the area of the range of what we have the solar system. So this is what Plato tries to cover. Too specific. But what Plato is trying to cover is this area. So if you look at these stars, these are all the big stars that have planets detected. If we limit to the planets detected with orbital periods above 80 days, and you can think the Earth is 1 year, we have very little. And this is what Plato will basically try to do, create a catalog of planets that are in the habitable zone, which is not too close to the star, which is too hot, not too far away, which is too cold or is more gaseous, in this area, because these are the most likely planets to host similar environment like ours. How do we do that? We do that by looking with the satellite to the same place in the sky for 2 years. So the operations are rather boring, because we just look on the sky, we look for 2 years, and we look at from 50,000 to 100,000 stars at the same time. And the idea is to try to get the statistics. So we have selected 2 fields. We will look in the southern sky and the northern sky at 2 different fields, and we stay there pointing 2 years in one field, 2 years on the other one. And this is the field we have selected for the first year. We're trying to avoid the large Magellanic Cloud, which is an area with a high number of stars, and it's now to the most interesting thing, which is the mission. Let me go here. What is the operations concept? It's a single satellite, Plato, launched with Ariane 6, and that operates in the Lagrangian point 2. It's a point 1.5 million kilometers from Earth that is shadowed by the sun continuously. So the satellite can have the sun all the time on the back and point stably to some place on the sky. And also it's temperature-wise very stable, so you don't have fluctuations, thermoelastic fluctuations. It generates quite a lot of data. You will see why in a moment. Around 400 gigabits per day, which at this distance, this Lagrangian point is 1.5 million kilometers from Earth. So you don't have contact continuously a few hours a day due to the availability of stations. You cannot use them all the time. And it's difficult to get all this data down. So we compress data and so on, and we transmit around 430 gigabits per day, and we have an uplink for commanding 26 kilobits per second. The way the system is composed is a traditional ISA mission. I don't know how used you are to the missions and how we operate them, but we have normally a satellite or several satellites operate by a ground segment. And we have in ISA, we have the operational ground segment in Darmstadt. That is the one that controls the satellites. And then we have a science ground segment. So this one controls the operation of the satellite and gets the data. It's sent to the ground segments, the science ground segments, which process the data, generate the catalogs, and this is based in Madrid. Then we have also, in this mission, we have agreements with ground-based observatories for this additional data that we will put together. So we have observatories all over the world that will observe the same targets that we observe. This is how Plato looks like. it's a bit dark. Plato is designed to be done, instead of doing a very big telescope, the idea is to cover a very large area of the sky. If you want to do a very large field of view telescope with a single telescope, it's quite difficult, and also you need a huge focal plane, which it's quite difficult. So what was decided at the time was, instead of that, we have several telescopes. So we have 24 telescopes with one cadence and 2 that are faster. Each telescope has 20 degrees field of view, and the field of views overlap. So 6 telescopes in a group point to the same area on the sky, and when we average the data from all 6, we improve the signal-to-noise ratio. The spacecraft is 2.5 tons, more or less, which is close to the launcher performance Ariane 6 now to go to this Lagrangian point. They are about that amount. It requires 3 kilowatts of power, and that's why you have these long solar arrays, and this is all to power the camera. Let's give you an idea of the size. I think I have it on the next one. It's around 9 meters once deployed by almost 4 meters. And it's composed, the design is made in a way that you separate thermally the bench where the cameras are mounted to the platform. The platform is here below, and I will show you pictures now. And it has basically a sun shield on the back that also includes the solar arrays. Let's say this is a 3-axis stabilized satellite because we point always to the same place. We have a high-gain antenna. We have monopropellant thrusters for active control. So we'll not go into details. On the design, it has to be light. So all this structure is in CFRP, the carbon fiber reinforced plastic, which introduces certain complications as well. You have to be careful. This material is hygroscopic. Gets water, and especially for the CCDs or detectors, it releases a lot of water. If you think James Webb had a structure also in CFRP, and after launch, you generate a cloud of around 25 kilos of water. Here is a bit lower, but it's still 10 kilos of water. So you have to make sure that your detectors are not the coldest point. Have condensation that will affect your transmission. This is built the structure of these science missions is always the same. We have normally a contractor that does the platform, and this is industrial. While the cameras are built in a collaboration between ESA and institutes. So it's institutes and industry working together. On the spacecraft side, Plato is led by a core team. We call it led by OHB in Germany. They are the prime. With Beyond Gravity, which is the old RUAC, for the ones that are familiar in Switzerland, that is doing the structure, and Thales Alenia Space, both in France and the UK, that is building the avionics of the spacecraft, and with a lot of industrial partners all over Europe for the different components. Plato doesn't have any collaboration with the US. This one is purely European. Here you see the team on our last progress meeting. The payload, instead, is built by ESA in collaboration with institutes. The way it works is slightly different. So a country puts money to develop a part of the payload. Let's say nationally, the UK Space Agency say, we will do this. We'll do the electronics. And the Spanish Space Agency will do something else, or the French. What is the interest for these national contributions? The interest is 2 things. I mean, normally they do it to develop their own capabilities, but also because this contribution comes back into access to the science, privileged access to the science. What it means is, okay, the members, countries that contribute, the scientists from those groups, they have the data for themselves for 8 months. ESA missions, by default, the data is public, but you have a proprietary period, which is 8 months in this mission. Other missions is 1 year. And this is where in some missions the Nobel Prize is for the scientists. So the interest is access to the science privilege if they do these contributions. but also they are interested in developing also hardware. Now, let me just show you. Each one of these cameras, as I explained, at the end, they have overlapping field of views, and they cover altogether around 2,000 square degrees of the sky. These cameras are big. This is 1 meter something. The optics is 20 centimeters. And they are composed of, basically, picture a series of lenses. So it's a transmission system. Installing a tube, and the tube has outside heaters, and these heaters actively focus the telescope. So we use the heating to actively change the distance between lenses and heat. They focus the light on a focal plane assembly, and each focal plane assembly contains 4 detectors, and these are your detectors. These are the large detectors. The 4K by 4K, I think, is the largest that we have flown in ESA missions so far. And if you think, so we have 4 in each of these cameras, 4 4K by 4K, multiplied by 20, we are flying 100 plus CCDs that you deliver. And this combined, if you want, is the largest focal plane that we have in space. It's larger than Gaia. Then there's an electronics box that controls the detectors, and this is built by MSSL in the UK, here the Muller Laboratory. Then we have a series of electronic boxes. I will not go into the details, that are the ones that basically take from all these cameras the data. They process it on board because we cannot download all the images. We don't download the full frame images. We select the targets, we process on board, we take these cutouts of the images, and we send them to ground. And then all of this space wire network that basically takes the data, compresses it, puts it in mass memory, and sends it to ground. So the payload is a combination, it's a collaboration led by ESA, so I'm managing the payload, but the collaboration is 120 institutes, plus many more doing the science data processing on ground, together with industry and all the different partners that collaborate. So it's a big thing. Now, the structure of this one is, we're not going into details, but it's basically managed by ESA with collaborations from all these institutes on the different countries. So we have some areas are institutes, some areas are industry, like yourself, Teledyne for the detectors, but in many cases are University of Bern, INAF is an institute in Italy, we have the Catholic University of Leuven, so it's a collaboration of institutes all over Europe. Also for the electronics, it's the same. We have DLR, it has a big contribution. And we have University in Paris, the Institute of Astrophysics in Spain, etc. So this one is a partnership, is with institutes. Very big as well, like all of this large collaboration. There's a picture from a while back already. Now, where are we? This is the design. Fine. I wanted to take the opportunity to show you a few pictures. The critical items for this mission was always, we have to manufacture many devices, many CCDs, many lenses, integrate the cameras, and test them. There were some doubts, first on the capability to do a mission with all this kind of serial production, not so much on the part like yourselves, because you're an industrial entity and you can build the CCDs. But then the lenses and the testing, it was done by institutes. And the big question is are universities ready to do this in a serialized manner, to build 20, 30 cameras almost with the spares, to test them, to characterize them, and so on. And this has been always the biggest risk. But the teams managed, I think they did quite a good job, and they managed very well. Your CCDs were delivered very early on, so this one was mitigated, but then the teams have been working for years doing the other steps, and they needed to continuously, during 3 years, continuously integrate and test cameras. Where are we? We have done all the typical development models, an engineering model, a qualification model, the flight models, and this is where we are now in pictures. This was the first camera, a structural model that we tested, a 3 years back, where we did a full characterization test of the camera. The detectors sit here to make sure that it passed the qualification. So we qualified one of the cameras, and it was okay. And also we did a test of all the electronics. This is the bench that showed with an engineering model how the electronics communicate with each other. And for example, here the CCDs built by yourself are here. And this proof that we can talk with one chain altogether. Afterwards, we had a qualification model of the full optical bench. This is the vibration test done at a test tech. These are cameras that are representative mechanically and thermally, but there was no CCDs here. It was just a mass representation, but we had the optics inside to make sure that the optics survive. So this was done. The amount of cabling that you have for all the cameras on the back is quite big, and this is posing quite a problem to try to manage it. After that, we took this and we did a thermal test, because with the accuracy that you need to achieve, one of the important points is the amount of thermoelastic deformation. You have to make sure that under the operational temperature, we operate around -90, that the deformation is controlled, because otherwise you will affect the science. The deformations we want to measure are very difficult to measure on ground. So what we do is we exaggerate the situation to try to measure something that will be larger than what we expect in orbit. So we did this test. This is the I don't know if you ever see it. This is we call it the Large Sun Simulator in ESA. It's the biggest test facility in Europe, where you can place a full satellite inside. Normally the satellites are a bit smaller, so you can also even open the solar arrays. And you have a sun simulator. So if you need, you can simulate the sun illumination to test solar arrays. Here we were just doing a thermal test, and we did also tests during cold with thermogrammetry, just to look at the deformation. Just to give you an idea, then we take this PLM, the payload module, and we integrate it with the spacecraft. So this was all a structural thermal model, but it was to prove the concept. This was done 1.5 years ago. And the idea was to prove the concept on which we mount the spacecraft onto the payload module. And both activities can work in parallel and detached. This was key to keep the schedule, because if one delays or the other one delays, we are not stopping each other. In principle, you can build the whole spacecraft on one side and the payload on the other side. And mating it takes a long day and a half. So this was with the structural model. Then we took it to do the acoustic test. This is a chamber. This is the acoustic test chamber. What you see here are big loudspeakers that just generate acoustic excitation, and that simulates the launch environment and also qualified the system. This is important because at the beginning in many missions, you put requirements, and as the requirements are flown down, then what reaches the detector is, if you put margins at every level, so the detector has to survive 300 G, which is, it's an overkill in terms of engineering. If you do this early enough, you characterize the levels. And now when we tested the flight hardware, we didn't have to test to these 300 Gs, because you raise the risk of breaking something or over-engineering it early on for something that is not real. And what we have measured, for example, in terms of shock, is 10 G at the interface. So the detectors will see almost nothing. That reduces the risk. So then at the spacecraft level also, we did a bench. This is the avionics bench to show that everything communicates together. So this was all, let's say, development models. Now on the space segment, the avionics panel of the spacecraft is now finished. This is where the communication system, the computer, transmission system, everything is here, the AOCS. And this has been completed. I will show you just pictures. And basically, this is the structure and the avionics panel that goes below that were ready for mating. These are the two pieces together, and I'll show you a few pictures. This was in Cannes a couple of weeks ago, where we mated the spacecraft panel. So the spacecraft is is almost finished, let's say. This is the final steps of mounting. You see the people here connecting the harnesses and bringing everything together. So, and this is the final connection. So we have here the spacecraft finished, pending the outside panels. The sun shields are also completed. And this is the last step. We did the bakeout also 2 weeks ago. So all these solar panels, this 9 meter by 3 meter, were completed, finished, and this is in the chamber where they are baked out and tested at cold. It was also done in vacuum, so it's almost finished now. Let's say. These are the panels individually that will be mounted. What about the cameras? So for the cameras, let me see, show you the picture. We built all the focal plane arrays. Here you see the size of one. Here it has 4 CCDs of the ones that you have produced in a focal plane. Focal planes that have been also assembled here at Teledyne. We didn't not only manufacture the CCDs, but you guys also put it together as a focal plane. And this is, we did half here, more than half here, and some other ones in Spain. So we need 26 cameras, and they are all these parts are completed. All the electronics by MSSL are completed. All the cameras, the telescopes have been delivered, and also the testing of the analog chains with the CCDs for all of them have been done. So this was a major achievement because it was a big risk on the mission, and now it's complete. And we have plenty of these cameras ready to be integrated on the Prime. Let me show you. In theory, we have delivered them all. We test them all as well. We test them at cryogenic test campaign of all the cameras in 3 different test houses, and we show that we can control the temperature around the design point. This is the important thing, because in orbit, if we need to tune the temperature, you want them to be around the center. So this shows that the best focus of all the cameras is around -80. And I just go to a picture. You may see in the news or the press, you will see when they come, every camera, according to the scientists, was given a name. The idea was every country selected scientists that contributed to the exoplanet research. So also it's much easier to track cameras now than numbers, because numbers start to be complicated. We were discussing, this might be the tube number 20 that connects, in theory, to the focal plane number 20, but then there's a delay here and there. Now it's the focal plane number 16 that has the camera number 14 with the tube number 20, that it will be in the hole number 19, because the hole is fixed with the harnesses to a channel on the electronics. Complete mess. So we use the names, the proper names, and they are all, as I say, they are all of scientists, all scientists that have passed away, that contributed to the exoplanet discovery. There was a big discussion between the scientists which country will define the first one. So we chose Hypatia, which is classic. It's not any particular country, but basically this will be used also for PR and communication with the teams managed to deliver 1 camera every 5 to 6 weeks, and this is it's a very big thing, meaning assemble and test every time. So we were quite happy. We were already populating the bench. These are 3 mounted, and I have another picture where we had already 11 mounted with all the harness on the back. Then I will show you a few problems we had, because not everything is going so well, like always. At the last moment, we had some late issues. First one, in the very last camera, pretty much after the thermal cycling and after the bakeout, this is what we saw. We saw the detector, and the guys on the team that are involved, they see it. What you see here, this is a frame transfer CCD. It's a CCD from the ones you produce here, with one area that is metallized. And what you see here is this halo, this haze. There was some contamination event on the chamber that was not seen before. So something has basically outgassed. It's not very clear still what it was. There were different samples. Some of them show residues of grease, but nothing has been traced in the chamber. Some others show other hydrocarbons. So this obviously was not worth for flight as it was. So there was another bakeout done. The bakeout has eliminated the contamination of the the CCD, but of course we are still trying to figure out where it came from. But in principle, the CCD is now good for flight, the focal plane, with the 4 CCDs. But this was a very late thing that after 24 cameras we were okay. This one, which was tested in another facility, was not okay. So, one example. Another one, very unfortunate, we did the qualification of the heater bonding of everything. Just by chance, we opened the MLI of one of the cameras and we saw the heater delaminate. That's bad. We have looked at the qualification. The qualification was done properly. Maybe it didn't have the right curvature of the surface where we applied it. Maybe there's an issue with the glue. So now we have all the cameras manufactured and tested, and with the MLI installed, you don't want to get rid of this blanket. What we did is we opened kind of windows, trying not to contaminate anything. We create cutouts in which we can access to inspect all the cameras. And we saw that half of them, only one had this big delamination, but the other ones have a little bit of detachment on a corner. So we cannot afford to take the risk, but also we cannot redo all the cameras now because we don't have blankets for everything. So we are looking at solutions to secure the heaters, even with tie wraps or tape, but this has to be qualified, has to be compatible at cold and so on. So this is what we are doing now. But we found a solution that we will repair the cameras in 3 weeks. Fortunately, but it was late. Another thing, looking at the optical testing, we do optical testing at subsystem of the focal plane. And in some of them, this is a Harman test, we call it. We see some dots missing. That means it was very strange. We could not figure out what it was. Then analyzing the camera images and so on, we took other images. We saw that there was kind of a feature. This is from the spider of the illuminator. That's okay. But this feature is strange. We opened one camera and we saw that, okay, there was one error of the FHP, the company that installed the MLI, routed the cable around the wrong place, and the cable is going on top of the lens. So somehow this is a shadow. Okay, it's very easy to resolve. You move it away, and we routed the other way. But it's only on this one. It was a workmanship thing, so we could not take the risk. So we dismounted all the cameras, inspect them all, and indeed we found it in 10 cameras of the 24. So root cause, difficult to say. There was no stay out zones clearly defined here. When you are closing the MLI, you don't have good visibility, but it's very easy to say now, well, it's a big mistake, but I don't know how we'll have prevented it completely the way the system was designed, because the blanket is prepared outside, not to cut in the clean room. So now we repair the cameras, but we had to open, and the CCDs, if you can imagine, are here, and we don't want to contaminate them. So it was a very careful kind of surgery to be done in the last minute. So this is what we are doing now. And the last one that I don't have a slide, but unfortunately during the integration of the very last camera, one operator dropped a laser tracker nest that we use for alignment on top of the focal plane. It hit one CCD, bounced on the next one, and rolled on the third one, killed 3 out of the 4. Fortunately, it never happened before, and we have a spare. We have another spare ones, but basically it's a big thing. But you can see that, of course, if you do 24, 25 things, and you multiply by the number of operations, the likelihood that at some fails is high, and you know that. Of course, if it happens at high level of integration, then it's a big problem. So we will solve these things. We have delivered all the cameras except the 2 fast cameras, because we have the last problem that I also don't put here. The last 2 cameras that needed to be tested have to be tested in Paris, and 1 month ago there was a storm. The river went up, flooded the lab. The water came to 2.5 meters to the ceiling. The test facility, it's 1 floor up. Okay, the chamber was not affected, but all the control system is destroyed. And the control system, the tanks, the nitrogen piping, the electronics, everything can be rebuilt. Many of it is built for purpose, the lead times for those things are months. So now KNES is telling us that the best they can do is 8 months. That in per se means 8 months delay on completing the integration, but not only that, in a big mission, you have to test it. And then you have selected a facility. If you miss the slot on the facility, comes another satellite. And a satellite program is 7-8 months. So this delay translates in 1.5 years delay on the program. So we could not afford that. So we are adapting 2 other test facilities in an urgent fashion to test the last 2 cameras. And this is what we are doing now. And we will test them by February. And then this will not affect the launch. But anything that you delay on these activities now are having an impact. So the closer you get to launch, the faster you need to implement a mitigation strategy. And we had backup because I didn't explain too well, but just to remind you, we have 2 types of cameras. These all are normal cameras, and these 2 are fast cameras. These are used also for fine pointing of the spacecraft. So they are a bit faster, so they consume more power. So since here we had many, 24, we had 3 facilities backup. If one fails, we use the 3 nominally, but if one fails, the other 2 can absorb the extras. This one, it's only 2, say, okay, we can afford the risk to have only 1 facility. And that facility is the one that gets flooded. So it's unfortunate, but it's a balance between a risk mitigation, having an extra facility there will have been very costly, and having an accident, which we did have. So the situation, yes, the electronics of the payload are also all delivered and completed. This is very good. The software is also progressing well. So just to show you that basically, in principle, we are still in line for a launch in December 26 because we have a contingency at ESA level maintained of 4 months. So if we can now deliver these 2 cameras in the next 2 months, which I think we should be able to find this extra facility, we can still launch in December 26. I think 4 months margin for 2 years is not too bad. The only open question on this one is the launcher. We'll launch with Ariane 6-2. Ariane 6-2 is delaying a little bit, They have problems, they have commercial customers. So maybe they want to delay us to January 27, but in case we did a compatibility study with Falcon 9. SpaceX has many more launches available now yet. So it could always be an option, but of course, we want to launch with a European supplier as much as possible. It's part of our endeavor also to promote the European industry. And this is the moment in which Ariane 6 has to really take all these future missions. So we are confident they will be there and that we will be able to, worst case, beginning 27. So it means that the mission, when we started here, 2017, you started way before with the development of the CCDs. We said we will launch December 26. And we are there. So Plato is on cost as well. We still have 20% of our financial margin and in schedule. And this is, for these big programs, is quite unique. And that's why it has been thanks to the work of all these institutes and your work, for example, that you have been participating very actively. This has helped maintain this mission quite on track. So we have all the eyes on us because they want us to complete it on track. So it was to give you an idea. I know it was a bit too extensive on all the spacecraft, but it was to give you an idea where we are. We are close to the end. I hope next time, if I send you something, it will be after the testing, and we will be getting close to the launch. I take the opportunity to thank the team here that did it, because really it has been an important contribution. Success. What I had. So, any questions?